I'm going to share my screen with you now and take you through a quick introduction to our course. So as I have already said, hello everyone and welcome to the 8th webinar of the Preparing for the PAT course 2023. My name is Kat, my pronouns are she, her, and I'm the Access Officer for the Department of Physics. That means that I run most of our programmes for secondary school students, including all of our stuff to support people like you who are interested in applying to study physics here in Oxford or elsewhere. This session is being recorded and will be made available to you tomorrow. Quick reminder of the housekeeping rules for those of you joining us on Zoom. You will be able to use the Q&A for any questions that you'd like to have addressed. I'll let you know when this is switched on and ready. You can also access the chat to share thoughts, but please keep it polite and kind. Don't share any personal details or information, and also don't use it for the questions that you want us to answer. Keep those in the Q&A so that you don't get them lost. I'll switch on the chat after I've done this introduction. If at any point you're feeling unsafe or concerned about anyone, you can contact our safeguarding lead or you can contact me. But in the meantime, let's get started. We are now in the final week of our course, but we have had a few people who joined just this week. A very warm welcome to you. For those people, I'll start with a very quick reminder of what the PAT is and what this course is. I won't take questions in this section. I'm just going to talk. And if we have any questions, we have time for that tonight at the end of our webinar. First things first, the PAT is the physics admissions test at Oxford University, and it must be sat by all candidates for not just physics, but physics and philosophy, engineering and materials science as well. Whichever department you are applying to, your PAT will be marked by academics from that department. Your results on the PAT form part of the information which admissions tutors use to decide who is shortlisted for interview. To sit the PAT, your school have to be registered as a test centre and you must be registered as a candidate. That process has now closed. In the vast majority of countries, the PAT this year will be in a hybrid format with test questions on screen and a paper answer booklet will be scanned and returned to us for marking by your teacher or whoever invigilates. The online test will include a built-in on-screen calculator, and there is a trial version of this online now so that you can practice with it. This webinar is part of the PAT preparation course, which we run on behalf of all the subjects who require the PAT. This course consists of 8 webinars, along with problem sets and summer assignments, and we hope that you've got all the information you need to take the PAT, help you prepare for the PAT and be confident going into interviews if you are shortlisted. This week, 2 of our students, Nina and Aggie, are going to take you through their solutions to problem set 4, and I will then answer any last questions that you have about the PAT and any questions you have about next steps in the admissions process. Don't worry if you can't find all of our stuff. I'm going to share the link to problem set 4 in the chat once we get started. All of our previous sessions and materials are available online on the PAT course materials page, which looks a bit like this. The introduction to physics problem solving, which is right at the top, is a detailed look at some of the concepts which we discussed in our first webinar. And then underneath there are links clearly labelled to all of the webinars set out in order along with their associated problems and problems that we solved in advance of the next session. This page is updated after every session. We're almost at the end with just one more session waiting to be uploaded. You should be able to find all of the information that you need. Finally, just a quick reminder that all of the information that both you and your school need over the next couple of weeks as we move on from registering you from the PAT to getting you to sit the PAT and handing in your UCAS forms can be found on this page. I'll share the link again in tomorrow's morning's email. This is the most up-to-date page and it's the one to check first for any information that you need. It also has an excellent FAQ page, which is really useful. And just one more note, the test format, which I mentioned earlier, is a new one, but it's not as big a change as it might feel like. The questions will be really similar. The syllabus is unchanged. Even though we know it's not a big change, we don't want anyone feeling anxious. And as I already said, you can access a trial version of that test so you can see what it looks like in advance. And we'd highly recommend that over the next couple of weeks, you just have that page open and you use our on-screen calculator instead of your own so that it becomes second nature to you. That is my very quick PAT introduction and update. I hope it was helpful. I will take any questions at the end. For now, I'm going to stop screen sharing. I'm going to hand you over to Nina and Aggie while I move over to the chat and the question and answer to moderate. So let's do that one step at a time. Stop sharing my screen, and a big welcome to Nina and Aggie, who you can probably see on screen now. They are going to be sharing their own solutions to problem set 4. I am now going to switch off my camera, mute my microphone, and share those links so that these guys can do their thing. Thanks.
So I'm Aggie, and I will be going through the odd questions, and then Nina will be going through the even questions. So let me just share my iPad screen. There, you should be able to see my iPad screen now. I mean, if you can't see the screen, let me know in the chat. I guess that's easier. But yeah. Okay, but I can't see my screen now. That's okay. There we go. I can see my screen now. So the first question that we're going to do is a very common question. For example, if you do further mechanics and further maths, but it goes like this. So you have a smooth marble that is initially at rest at the top of a much larger smooth hemisphere of radius r. So the marble, which has some sort of tiny, I don't know, radius, because the sphere is so big, we can sort of, treat it as a point particle because the sphere is just so extremely big. Nice. The marble is given a slight nudge and begins to roll around the hemisphere. So part A asks, at what angle from the vertical will the marble leave the surface of the sphere? So let's just sort of write down all the forces that we have on the marble. So we have a marble here, and the marble has some mass m, which is going to be important. Then this is going to be the radius r because it's a hemisphere, so the radius is r everywhere. Then the marble, as it travels down, eventually, it's going to reach the stage at which it leaves the sphere. So let's draw the force. So we have n, we have the gravity, which is pulling it down, and let's just kind of, draw a bit of other stuff. So theta, r minus h, and h, where h is the initial, height of the. So h is going to be the height. So I mean, I'm just going to say that this is r minus h. So then you can see that the height at which is going to leave, which sorry, I forgot what the question was asking. It says at what angle? Okay, fine. Well, we're just going to define h here, r minus h here, just for the purpose of keeping it simple. So anyways, continuing on, we can now see that this is what the diagram looks like, and the marble is going to leave the hemisphere when the normal reaction force is equal to 0, because if the normal reaction force is equal to 0, then the only reason that you feel your weight at all is because the normal reaction of your floor isn't 0, right? So if the normal reaction force is equal to 0, that's when it's going to leave. You can kind of consider it as like the marble, pushing against the sphere less and less and less until it just doesn't push on it at all. So that is the case that we're going to be working with. Nice. And the marble is going around as, a sphere, which, if we just draw it in the 2D plane is going to have some nice circular motion. So let's kind of write down a force equation here. So we can see that if I'm going to resolve the forces, so I have the forces which are acting in the direction of the radius and the ones which are acting away from the radius. I know that the total force acting inside is going to be mg cos theta minus n. And that is going to be equal to the centripetal force. And we know that formula for that one is equal to mv squared over r, where v is the velocity of the marble. Nice. So we have one equation, and we obviously know that when it leaves the sphere, so when it leaves sphere, actually it's m is not equal to no, okay, never mind. So when it leaves the sphere, we know that n is equal to 0, so we might as well just write that mg cos theta is equal to mv squared over r. The m's cancel out, so we get that cos theta is equal to v squared over gr. So we have an angle, but obviously we don't know what v is, so we need to kind of find what the velocity is, but we can do that through energy conservation. So we know that initially the marble is going to have just a potential energy equal to mass times the gravitational field strength times the radius, because it's just at the top, is just nudged from the top, so we can say that it has no speed and the only energy it has is the gravitational potential energy. When it leaves, it's going to have energy equal to the gravitational potential energy, which is mg times, r minus h. Sorry, not r minus h. Yeah, r minus h, because that's how far it is from the ground, which is just here. Plus, obviously, it's kinetic energy, which is a half mv squared, and we can equate these equations and get mgr is equal to mg r minus h plus a half mv squared. However, r minus h, if I just do some simple trigonometry right here, I am going to very kind of to make sure that we get for everything, but you can see that is going to cos.
Oh, we lost you a little bit there, Aggie, just to warn you.
So we can rewrite out my whole equation. The mgr. Sorry. Oh, sorry.
No, it's okay. I was just letting you know your audio had gone a little bit funny for me, so you might need to repeat that bit. Thank you.
Okay, so anyway, I'll get back to the energies. So anyways, to kind of sum up what we did in case my audio cut off at any moment, we basically wrote down a force balance equation for the centripetal force, and we knew that the marble leaves the sphere when n is equal to 0. Sorry, I'm just going to close some apps, hoping that it's going to be a bit quicker. My Wi-Fi is going to be a bit quicker because I have a lot of stuff open. Okay, anyways, so we said that the marble is going to leave when the normal reaction force is equal to 0, and we found some sort of equation for the angle. However, as a result, so the energy at the point where it's is just the gravitational potential and kinetic, so mg r minus h plus a half mv squared. And right now, what I said here is I can just use trigonometry to find exactly what r minus h is equal to, because I don't know what h is and I want my formula in terms of stuff that I know. So I just get mg r minus h here, plus obviously the kinetic energy. And then I plug in the trigonometry that I was talking about, which is just r cos theta, because I have my hypotenuse and this is the adjacent side and I want the adjacent side. And I get that, so I get this sort of equation. Once again, all the masses are going to cancel out. And I'm left with gr1 minus cos theta is equal to a half v squared. I can rearrange this to get v. So I get v squared is equal to 2gr1 minus cos theta. So I have another equation in terms of v. So I have equation 1 and equation 2. Is my audio okay now?
You are back for me, Aggie. All good. Thank you.
Okay, so like everything I've said so far, like since the cutout, you've heard me.
Yep.
Okay, that's good. Thanks. Anyways, so that's good because that means that everything is okay. Nice. So I have my equation 1 for the velocity and equation 2 of the velocity. So as these things go, I want to solve them simultaneously. So I'm just going to take my equation 2 and put it into equation 1. So 2 goes to 1, and I get that cos theta is equal to 2gr1 minus cos theta over gr, which again, just simplifying this through, cos theta is equal to 1 minus cos theta. And then I can rearrange this so I get that 3 cos theta is equal to 2. So I get that theta is equal to cos to the minus 1, 2 over 3, which ends up being 48 degrees. So that is kind of the question. I'll zoom out in case anyone wants to kind of screenshot it or whatever. And like if people are not sure about some kind of detail of it, then I'm asking the Q&A, and then when Nina's doing the second question, I can answer it. But now we're on to part B of the problem, which says, how far away from the base of the sphere will the marble land? So what happens is the marble is going to leave the sphere. I'm going to copy this diagram paste on the next page. What happens now is the marble is going to leave the sphere, is going to travel at some sort of velocity, at some sort of angle, like so, and is going to, land some distance, I don't know, d away from the center of the sphere. And that is what we are going to work out. So it might look intimidating, but it's actually nothing new, nothing different that you have found, no different work than you've been doing in your regular Suvat equations. So this is the equation, and I know what my velocity is when it leaves. Sorry, I don't know my velocity. I know the angle that when it leaves is equal to 48 degrees, because that's what I worked out in part A, right? I also know right here what my velocity is going to be. Paste. So I know that my velocity at the point which it leaves is going to be equal to v, the square root of 2gr1 minus cos theta. And using the fact that actually cos theta was equal to 2/3, which I think is, 2/3, I get that the velocity is equal to 2gr1 minus 2/3, which is the square root of 2gr over 3, if I am correct. So that is the velocity at which it leaves with, and I also know the angle at which the angle with which the velocity is located at, because that is just theta. Sorry, no, that's I need to do a bit more work on that. So you can see that the marble is going to travel along the hemisphere. So it's just going to go like this, which means that when it leaves the sphere, is going to stop following the sphere. It's just going to start following its own velocity, which is going to be a tangent to the sphere at the point which it leaves it. So now I can work out the kind of theta of the velocity, the angle which the velocity is at, if I just draw this diagram. So, oops, that is a very not straight line. So I know that this is theta. I know that this is going to be perpendicular. And then I want the angle that my velocity is going to make right here, right? So kind of let me finish this triangle up. So I know if this is equal to theta, and if I finish this triangle here, this is equal to 90 degrees. Right here, this is equal to 90. Because angles in a triangle add up to 180, this is going to be 90 minus theta. And because angles in a straight line add up to 180, I know that all of this is going to be 180. So if I just call this alpha, I know that 90 minus theta plus 180 plus alpha is equal to 180, which means that 90 minus theta plus alpha is equal to 0. So I get that alpha is equal to 90. It's equal to something is not quite right. So 90 minus theta. Yeah, okay, so it's equal to oh yeah, sorry, I don't know why I said that this was 180, because this angle is clearly 90 degrees. Okay, so this is 90, this is 90. There we go. That makes, so this is 180. Yeah, this angle is 90. I was just made a little mistake there. So now I know that the 180 cancel out, so I get that alpha is equal to theta. Good, fantastic. I know what theta is, so I know that essentially, if I kind of reduce the problem to its main components, I have a ball which leaves the surface of the sphere with a velocity v at an angle alpha, like that. And obviously, sorry, I should probably stop saying obviously, because it might not be obvious. It's just kind of my catchphrase. This is going to travel some distance d, right here, like so, d. And let me just see how far away from the base will the marble land. Okay, how far? Okay, so we're also going to be needing this little distance, but we're going to firstly work out what d is. So from the point at which it's going to leave the hemisphere, we need to find out where it's going to land, because it's going to follow your regular parabolic motion. Okay, so using our Suvat equations, we know that if I look at the velocities horizontally, vertically, my s, my displacement, is just going to be equal to what I called d right here. My u, so my initial velocity in the vertical direction, so this velocity here, is going to be equal to minus v sine alpha. Now, I said minus because what I'm doing is I'm saying that going up is positive and going down is negative. You could obviously say that going down is positive and going up is negative as long as you stick to it. Then my final velocity, I don't care about. My acceleration is just minus g because it's the acceleration due to gravity. And the time, again, it's something that I will need, but for now, I don't know what it is. So that's my equation vertically, and horizontally. there is no acceleration because gravity just acts vertically. And I know that then, sorry, no, D is actually not what, yeah, this is actually clearly not D because I want the vertical displacement, which is going to be equal to R minus H. Apologies for that. Actually, it should be minus to that because I said that negative is going down and positive is going up. But I should probably just replace that with minus R cos theta because that's what I said right here, that this kind of height from which it falls is going to be equal to that. Nice. So horizontally now, I know that the distance traveled is going to be equal to the horizontal velocity times the time. So I know that the distance traveled is going to be equal to V cos alpha times the time. Okay, so I kind of know what I'm working with. Let me just rewrite the Suvat equations here in a more nicer way. I mean, these are not equations. I'm just writing out the key facts because I know that cos theta is equal to 1/3 and theta is equal to alpha. Just, sorry, not 1/3. It was 2/3. Nice. So if I just write it here, I get minus 2r over 3 minus v sine theta. Then we don't care about this. We have minus g and we have the time. So you can see that if I want d in this equation, I need to find t because I know what v is, I know what alpha is equal to, and I know what, yeah. So what I want is I need to find t using the vertical Suvat equations. So what I'm going to do is use the equation where we have s is equal to ut plus a half at squared. I'm going to put in all my variables. So I get minus 2r over 3 is equal to minus v sine theta t. Let me just check if I'm doing it the right way, not confusing too many people with the solutions. So okay, yeah, I am doing it. I was just doing a bit of a sanity check. Nice. So I have this equation right here. So yeah, minus v sine theta t minus a half gt squared. Okay, I'm going to go on to the next page and kind of write it out a bit nicer, like so. Now, so this is my equation. Let me just kind of get rid of the minus. So v sine theta t plus a half gt squared. Now let's kind of plug in what I know. So I know that v is equal to, let me just scroll back. V is equal to this. I know this is a very, very long question. So if there's anything that you're confused about, then obviously I can answer it after I finish going through the question. So I know what V is, and I know that cos theta is equal to 2/3. But I know that sine squared theta plus cos squared theta is equal to 1, which means that sine squared theta plus 2/3 squared is equal to 1. And now I actually need my calculator, which means that my sine squared theta is equal to 1 minus 2/3 squared. So 5/9. So I get my sine theta is equal to root 5/3. So I have all my information, plug that back into my formula once again. So I get 2r over 3 is equal to the square root of 2gr over 3 times this root 5/3 t plus a half gt squared. So I have a pretty horrible quadratic equation. Let me just kind of rearrange it in a way that you're familiar seeing your quadratic equation. So I have g over 2t squared plus the square root of 10gr over 27t minus 2/3r is equal to 0. And I want t. So what I have to do is I have to solve the quadratic equation. But this is a nightmare. There's clearly not a very easy solution to this. So you just have to plow through the quadratic formula, which I'm kind of going to spare you the pain of doing. For people who don't know, I'm just going to put it here. So t is equal to, so I'm just going to write the regular form that you've already seen in school, that x is equal to minus b plus minus the square root of b squared minus 4ac over 2a. And again, like the PAT, you do have the calculator in the PAT. However, this is all written in variables, you know, r and g, which you don't know what r is. I mean, you know what g is, but you don't know what r is. So you have to kind of use the quadratic formula here instead of just putting it into your calculator. And if you solve this, you get that t is equal to the square root of 2r over 27g minus 5 plus minus the square root of 23. Now we have two solutions for t. So you must be thinking, well, which solution do we pick? Well, time is positive in our problem here because it's going to flow forwards in time. The ball is obviously going to land after it has left the sphere. So we're going to pick the positive solution, which turns out to be the one with the positive sign, obviously. So we have our equation for t. Now we want our final expression, which is for the distance traveled. So d is equal to v cos alpha, which once again, using the fact that v is equal to the square root of 2g r over 3, and theta is equal to alpha, and cos alpha is equal to 2 over 3. This can be wrote as the square root of 2g r over 3 times 2 over 3 times the time, which we have just found in the above, so 2r over 27g minus 5 plus the square root of 23. And we get that our final solution for the distance, just for this kind of distance, because we still have a bit more work to do, is going to be now, so we have r, and then let me just kind of quickly, it's going to be 4r over 27 root 23 minus root 5. So that is, so we're almost there. So we have our distance from the point to which it leaves, but the question asks us for the distance from the base. So let me just copy and paste the diagram, which I have right here. So the distance which I have to subtract, or in this case, add, because I've just found d. However, we want this big long distance, L. So the distance that I want, so in order to do that, I need to find what this is. Well, actually, I need to find what this is and just add it to d. But I can just use Pythagoras, because I know what well, I don't even need to use Pythagoras, because I know that this distance is going to be the same as this distance. And using trigonometry, this is the opposite side, and I have my hypotenuse here, so I get that this side is going to be equal to r sine theta, and by default, this is going to be equal to r sine theta. So my total distance, which I'm going to call L, is equal to d plus r sine theta. And as I discussed before, let me just kind of get back what I said here. Sine theta is equal to root 5 over 3, like so. So I get that my total distance traveled is d plus r root 5 over 3, and put my expression for d, which I have here. Just copy and pasting because for the sake of conserving my energy, plus r root 5 over 3, and kind of adding them together, I get my final solution to be, well, there's not really like this, it's kind of as nice as it gets. That is kind of the nicest solution that you're going to get. Because you're going to get a pretty horrible fraction once you add the 1 over 27 and 1 over 3. But that is the final answer of how far. And I think, no, I've just realized I misinterpreted it, because they want this they want this distance. Okay, they actually want this distance, not from here. I just kind of read it wrong. But I mean, we've already been doing this quite a long time, but all you'd have to do in order to find the red distance is you'd have to take away r from what I just wrote. So, you know, minus r, so the red distance, I don't know, L2, because I got it wrong, is just L minus r, because r is just the radius of the sphere. But yeah, I read it wrong because it's from the base, so I assume it's going to be this part of the base. But like if you wrote this solution and you said, oh well, I interpreted this to be the end of the base, I don't know, it's just sort of a bit funny wording. You wouldn't lose marks because, you know, you're just reading it wrong. But anyways, that's the end of question 1, which has been a bit long. I'll answer some questions in the Q&A now. Let me stop sharing.
Thank you, Aggie. I think actually a lot of the questions in the Q&A are from me at the end. They're quite Pat specific.
Oh, okay.
Don't worry, not too much has come through. Thank you.
Okay, yeah, because I just saw like 20 questions appear, but okay.
No, you're good. A lot of them are from me a little bit later. And
Okay.
I think really interesting that you barely used a calculator at all. And as you say at the end, hey, it doesn't matter that you flick that last bit. You just write that it's L minus R and move on. Thank you so much. Over to Nina.
Thank you. Hi everyone, my name is Nina, and I'll be going through the even problems. Just set everything up. Okay. So you should be able to see a screen and the problem. Hopefully not my face.
Yep,
Cool.
I can see both of those.
Thank you. So in this problem, you have a loop-de-loop and a car going around it. And you can already tell that this is going to concern energies because the car is going up and down in space. So this is the mindset, I guess. In part A, oh, this will be a problem. So in part A, they ask if the car starts from a ramp which is at the same height as the loop. So these two, this point is the same height as this point. Will the car make it around safely, and explain why? So again, in this sub question, you're not given any numbers, you're not given any parameters, so you're expected to give a general comment on what the situation looks like. And yeah, so the car starting from here, it has some potential energy because it's above where where it seems sensible to define the zero potential energy level. As it goes down the loop, when it reaches this point here, all of the potential energy is converted to kinetic energy. So this should be a pretty familiar concept. And then as it goes up, when it reaches this point again, this kinetic energy is transferred back to potential energy. And because this point has the same level as this one, all of this kinetic energy, which it had here, is converted to potential energy up there. Point is, at this stage here, the car has zero kinetic energy. This means that it'll just flop down. It can't continue with no kinetic energy. So yeah, the answer is no, it won't go around safely. Conservation of energy. In reality, it'll drop off even sooner because you have friction and stuff, so it won't even reach that point. But in an ideal case, it won't reach that point. It won't be able to continue safely. Part B is where you get to do a bit more maths. So Bob wants to find out if it's possible to do the loop with a real car. Cool. He has built a loop which has a 6-meter radius. So usually while I'm reading the problem, I try to write down all of the numbers I'm given, because like often how you build your equations is based on what you're given as numbers. So this could be a good clue what formulas you have to use. And his car will approach the loop driving along a flat runway. So in this case, we don't have the initial ramp. We just have a flat runway, the loop, and then flat again. So the car starts here. What is the minimum speed in miles per hour that Bob needs to drive at in order to perform the loop successfully? So the car starts with some speed v. So the question is, what is this minimum? What is the minimum value of this? And here I would either circle or write down miles per hour, because I would absolutely forget to convert to miles per hour at the end of the problem. So yeah, what is this velocity which is needed so that the car can go around? So what is the condition for the car to go around? What does that mean in physical terms? That means that when it reaches the top, it has to not fall down. So when the car is here, it has to be able to stay there and continue. The limiting case, so what we want is for it to stay, but in order to be able to quantify when it stays, it's similar to the marble on the sphere, right? It no longer stays when the reaction force from the sphere equals 0. Yeah, so this would be the limiting case which we're looking for. We want a normal contact force equaling 0. This is when it falls down. So a sensible thing to do would be to get an expression for this normal contact force. And it is a frictional force, which is the sum of all of the forces acting on a body. Yeah. So the forces acting on the car would be gravity acting on it, as well as, because it's going around the loop, there would be a centripetal force acting on it. So the formula for centripetal force, you should no, you're not expected to derive it, is mv squared over r. So in this case, we want mv squared over r minus mg, because they're acting in different directions. Of course, you can define your coordinate system and like this positive, this negative, or the other way around, doesn't matter. So one minus the other should be equal to 0. And this is super useful because it gives us the opportunity to find an expression for v. So this is v at the top. So let's call it vt. Be careful with notation, unlike me. So v at the top, so that the car doesn't fall over, or at the limiting case when it does fall over. So the minimum speed it needs to have up there would be if you just rearrange this square root gr. Cool. So we have the minimum speed which the car needs when it's at the top. We're asking about the minimum speed which it needs at the bottom. The way to do that would be, again, using conservation of energy. So we know that at the bottom, the only energy it has is mv squared over 2. So this is this v with which it starts. It has no potential energy because this is where we define our 0 line. And this should equal the the total energy at the end, which is the potential energy Vt squared over 2. The kinetic energy Vt squared over 2 plus mg, which is the potential energy times this height. And this height is just twice the radius, right? Okay, and now you can see that we have the v we're looking for. We have some parameters which we know, the m, the g, and the r, and we have vt, which we just found out. So by plugging this here and rearranging, we get that v with which the car should start equals 5gr square root of that. And if you plug in the numbers, this is 17 meters per second, which is about 38.4 miles per hour. I have to work on my handwriting. But yeah, so this is part B. Again, in this sort of questions, you are expecting to use conservation of energy, and in this case, this was the profound observation that this is the limiting case where the car does not make it, and therefore it's interesting for when it does make it. Part C, they ask us, is there any reason why Bob shouldn't go much faster than the minimum speed? So in this case, you will see these and this in number of problems where they ask you, okay, you looked at the idealized case, what happens in reality? And in this case, think about you going super, super fast in a car. If you're into like F1 or something, you would know about the existence of a G-force. So the G-force, when you're accelerating, like in a car or a plane or something, you have the perception of weight on you, right? You're pushed back into the seat. And this perceived weight is quantified through the G-force. It's a force per unit mass, I think. And if you experience a G-force which is too high for the human body, you might pass out or get squished, and yeah, it's not good for biological organisms to be under a big G-force. So yeah, he shouldn't go much faster than what is needed so that he doesn't pass out, for example, when he is on top of the loop. Yes, I think that's this question. I'm gonna answer questions in the Q&A, but yeah, let's move on.
Lovely, thanks so much, Nina. I think you've got a few questions waiting for you about centrifugal force.
No, so I will go through question 3 now. Sorry, there we go. So you should be able to see my screen. Yeah. So question 3 is also a centripetal force question, which I think all of these are. So a velodrome. A velodrome allows cyclists to travel at high speeds around tight corners since the track is banked at a steep angle. By drawing a force diagram, part A, by drawing a force diagram, show why this banking is necessary. Determine an expression for the maximum speed a cyclist can travel at as a function of the radius r of the corner and the coefficient of the dynamic friction nu. So the diagram that we are going to show is we have some sort of embankment, and that embankment is at an angle theta, and we have the kind of cyclist, which I'm just going to say is a ball, and we have the normal reaction force N. Yeah, so we have the normal reaction force N, and we have the friction. And now the friction is going to be acting inwards because the cyclist wants to slip outwards. Like the cyclist, if you think about what happens when you go really, really fast, you're going to feel being pushed outside. Yeah, and then we also have the weight of the cyclist. So what we have to do, well, this is the kind of the force diagram, which was the first part of the question, and you can see that the bank is necessary because if there was banking, there would be no frictional force because the cyclist there'd be nothing to cause the friction, because the only reason that friction ever exists is in order to stop something. It's in order to stop you slipping down, in order to, so there would be no frictional force acting to the left or in any direction in that sense. We would just have the reaction force and we would have the weight, which means that there would be no force providing the centripetal force in order for the cyclist to go around. So that is why you need the embankment, because if there was no embankment, there would be no centripetal force, so there would be no circular motion, and hence there would be just no motion in the velodrome, which by default has some sort of like circular shape. I don't know its exact shape. So that's why the banking is necessary. Determine an expression for the maximum speed that a cyclist can travel as a function of the radius r of the corner and the coefficient of dynamic friction nu. So let's sort of resolve the forces, because so let's resolve the forces, and this is going to be the direction in which the centripetal force is going to act. So we're going to firstly resolve the forces vertically, and those have to balance because the cyclist is not moving up or down. So we get that N. If I just kind of see that this is going to be equal to, just a quick explanation, a similar, like this, like once you do more questions, it's obvious, but I'm just going to kind of write it here. This is going to be 90 minus theta, because this is a right angle. So this is going to be equal to theta. So then resolving vertical, resolving all my angles vertically. So if I just, I actually don't need this theta. The theta that I want is going to be equal to, so if I just draw a line here, I know that this is going to be equal to theta, and as a result, this is going to be then equal to 90 minus theta. So if I have an angle here, it's going to be equal to theta, just to get the direction of the normal reaction force. So once I resolve all the forces, I get that n cos theta minus f sine theta. This one is more clear because you can see that the angle of the force is going to be theta because it's parallel to the bank. So you can see that the vertical direction is going to be minus f sine theta because it's pulling it down, minus the weight is equal to 0. So now we want the limiting case. So we want the case as it's just about to slip, in which case F is equal to mu nu, because as some of you know, that the general formula for the friction, I think it's F is less than equal to mu n, like so. So that's one thing that I can put in. So I know that n cos theta minus mu n sine theta minus the weight is equal to 0. And finally, the weight is just equal to mass times the gravitational field strength. So I get n cos theta minus mu n sine theta minus mg is equal to 0. Rearranging that, I get that n is equal to mg over n cos theta minus mu sine theta. And again, I'm saying that because the question asks what's the fastest speed, right? And in this case, the limiting case is going to be when f is equal to mu n. If, as the speed slowly increases, this is what's going to be satisfied. But the highest speed possible is when the friction is just as strong as possible. And if you increase the speed even more, it will just fly away. So that is kind of the limiting case. We're not going to have any kind of n is equal to 0 here. It's more friction that's limiting it, not the reaction force. So Now let's resolve the forces horizontally. So that's vertically. And now let's resolve them horizontally. So I know that n sine theta plus F cos theta is going to be the total force acting in the left direction, because you can see that I'm just going to have my F sine theta here and my F cos theta right here. Sorry, F sine, F cos theta, and N. So F sine, F cos theta, and N cos sine theta, like so. So this is my total force acting in the left direction, which also happens to be the direction that the centripetal force acts. So mv squared over r. Nice. So that is that part. Once again, I can just say that F is equal to mu n. So I get n sine theta plus mu n cos theta is equal to mv squared over r. So then I get that n sine theta plus mu cos theta is equal to mv squared over r. So this is equation 1, this is equation 2. I know what n is equal to, because that's what expression 1 is for. So let's just simplify it quicker. So let's just times by r and divide by n on both sides. So r over m sine theta plus mu cos theta is equal to v squared. So if I plug now expression 1 into this expression, so 1 goes into 2, I get that r mg over m sine theta plus, oh, I don't know why I put an n here, clearly that's not there, mu cos theta over cos theta minus mu sine theta is equal to v squared. And finally, just finishing this equation, obviously the m's cancel out, and I get that v is equal to the square root of sine theta plus mu cos theta g r over cos theta minus mu sine theta. So very ugly expression, and this is going to be equal to the maximum speed. Again, if you carried on having this inequality, and instead of putting the equality into it and went through with the inequality, you would get this at the end. And then you would be able to see that the right-hand side is going to be a maximum speed when you have an equality. But for the purpose of this question, as long as you explain your reasoning why you're going to start using the equality, it's just, easier to go this way. But that's kind of just for me to reassure you that why this is the maximum speed and it's exactly what they want. Nice. So the second part of the question is, determine the value of mu required for the bike to travel at 80 kilometers an hour around corners of radius 25 meters with a maximum banking angle of 42 degrees. So V needs to be 80 kilometers an hour. And we want mu equals question mark. We know that theta is equal to 42 degrees and the sort of radius is equal to 25 meters. So you can see that, let me just, you can see that, and we want to find mu. Okay, that's good. You can see that our expression for mu, what do we have? Oh yeah, sorry, I forgot to mention that when I said r, this r is equal to the radius of this circular motion. I forgot to mention that, which is equal to the radius of the track, which is what we are given here. I should have been more explicit here. Yeah, because r, obviously with circular motion, you go around a circle with some radius r, and yeah, this is equal to r. So everything is right, is nice, because that does seem like I put it a bit out of thin air. Anyways, we have our expression for v here, but this time we want mu. So what we're going to do is we're going to rearrange our expression for v to make it as mu is equal to. So v squared cos theta minus mu sine theta is equal to sine theta plus mu cos theta g r. And for the purpose of keeping this short, you guys can go through the algebra yourself. It's just rearranging an equation. I get that mu is equal to v squared cos theta minus g r sine theta over v squared sine theta plus g r cos theta, like so. I also know that g is equal to 10 meters per second. So you can see that I have a little bit of an issue here, because my r is in meters, my g is in meters per second, because, off the top of your head, I can't tell you what g is in kilometers an hour. But my velocity, which the question gives me, is in kilometers per hour. So what I need to do is I need to convert my velocity from kilometers an hour into meters per second. So 80 kilometers an hour is equal to 80 times 10 to the power of 3 meters per hour, because 1 kilometer is equal to 10 to the power of 3 meters. And an hour is equal to 3,600 seconds. Yes. So this is going to be equal to 8 times 10 to the power of 3 divided by 3,600 meters per second. You plug that, that's equal to around 22.2 meters per second. So that is the velocity that you want. So what you have to do here is, you know what your theta is, it's here. You know what G is, it's here. You know what V is, it's right here. And you know what R is right here. So what you do is you plug in all these values into this equation right here, put it into your calculator, which you have in the pack. So that's all good. And you get that mu is equal to around 0.40. And that is the end of the question. So I will stop sharing my screen.
Lovely.
Nice.
Thanks so much, Aggie. I think there are a couple of questions waiting for you in the chat, and we'll hand back over to Nina. Thanks so much. Sorry, in the Q&A, not the chat.
Okay. Yeah, there we go. So, in this problem, we have, again, cars, and they introduce us to the idea of spoilers, which direct air flow from somewhere which direct airflow over the car upwards. So this is the key part, that the air is directed upwards. This is the problem I should be doing, right? Yeah, I think this is the next one. So in part A, oops. There we go. In part A, they ask, explain why this makes the cars heavier with reference to at least one of Newton's laws of motion, which is already a very good hint. Because, as I pointed out, the air is pushed upwards. Newton 3 says that for every action, there is an equal counteraction. So in this case, it's sufficient to write down that when the air is pushed up, the car is pushed down by this motion of the air. And so they ask us why the car appears heavier. And when the car is pushed down, this means that the normal reaction is bigger, and then the friction that the car experiences is also bigger. And because of the normal reaction is bigger, if you put a big scale under the car, it will appear heavier, right? Its weight will be larger. So in part B, a student suggested this is a silly design feature, as the heavier object will go slower. Why? What is the physics behind this argument, and is it correct? The answer is that it's not correct, because the statement that a heavier object goes slower is not fundamentally true. What they're referring to is Newton 1, yeah, one of the Newtons, which says that the force is proportional to the mass of an object. Something which you'll do very, very good to remember for interviews as well is that this mass is the inertial mass of the object. It's just what it's called. And this mass doesn't change. So this is just the material from which the car is made. Yeah, it's the same mass the car would have in vacuum if nothing is acting on it. What changes when the air pushes down on the car, or if anything pushes down on the car, would be the perceived weight of the car by the earth. The earth would say, hey, this car seems heavier, but the mass of the car itself would be the same. And this is the mass which this law is interested with. So if this stays constant to reach a certain acceleration, the force would be the same if you push down or you don't push down on the car. So this is, the physics part of this question. And I guess you could mention that, as I said here, the friction, because it's proportional to the normal reaction, you'll have more friction, but this gives the car more grip with the ground, so it'll be easier for it to turn its wheels, and it'll actually make it easier to accelerate. So actually it's the opposite. So in part C, they say, assume that the downforce created from the spoilers is proportional to V squared. So let's call this downforce, let's call this Fn for F Newton, so that we can just call this F. So the downforce created from the spoilers is proportional to V squared. Oops. Where V is the velocity of the car. If it is possible for a racing car of mass 800 kilograms to drive on the roof of the tunnel, provided it is traveling faster. So it's at least 150 miles per hour. Again, whenever you see units which are not SI units, try to convert as quickly as possible, just to not start doing calculations with the wrong units. So this is about 67 meters per second. Determine the value of the constant of proportionality. So here, usually at an exam, you can say let F be K times V squared, and you're looking for K, right? Yeah, so this is the setup of the question. So what's happening? The car, it's driving on some roof. So this is the car, you have a roof. You know, you're looking for an expression for this F, right, in order to determine K. So the forces acting on the car would be the gravitational force. And so the air is pushing downwards on the car, but this is like in this direction because the car is driving on the roof. So it's flipped. So our F would be pointing in this direction. As before, the limiting case of the car being able to stay there, it is these two things minus, because they're in different directions, being equal to 0. So we know that kv squared we want it to equal to mg for the car to not fall. And so when you plug in your numbers, k will be 1.75. And yeah, and that's this question.
Amazing. Thank you so much.
So the next question I'm going to do is actually much more difficult to what you are going to get. So last year we went through it, and we couldn't think of the way to sort of explain it. So sort of kind of consider it as like a cool fact. But yeah, it's a much harder question than you would ever get in the PAT. Oh, I mean, that I would think would ever come up on the PAT. Don't, like, obviously I'm not promising you, because the PAT could be mean, but like in my opinion, you wouldn't come up on the PAT. But obviously this is my opinion just from doing the PAT and the tutoring, so I cannot be 100% right. Anyways, so the question is actually a very cool thing. So it asks, in Hertford, Hampshire, and Hereford, hurricanes hardly happen. However, if they were to happen, would they likely rotate clockwise, anti-clockwise, or have no preference? So let's consider the Earth, right? The Earth spins around its own axis with some sort of angular velocity. So we have a north hemisphere and we have a south hemisphere. And the question asks us, so which way hurricanes would spin in Hertford, Hampshire, which is all in the UK, so it's in the northern hemisphere. So the reason why hurricanes turn is because of something called the Coriolis force. So F is equal to minus 2m, and then we have the vector product of the angular velocity times the vector from the middle. Times the velocity vector. So let's kind of talk about this expression, because it's obviously something that you have not come about. You've come across the centripetal force, which is F is equal to mv squared over r. So is this force that you feel when you travel in a circle. The centrifugal force is also a force that you feel when you travel, when you have this sort of kind of I don't know what's the right word for it. Just kind of it's a force which happens because of rotating. Right, I guess that's the most easier way to explain it. Like the centripetal force, it's not a force which is actually, there. Like it's a force which you feel because of the fact that you are traveling, rotating, or going in a circle, as for the case of the centripetal force. So it's a force that you feel because you're spinning. It's not a real force like gravity or whatever. It's just a force that you feel by the virtue of the fact that you are on the surf rotating. So that's what the Coriolis force is. The mass is just the mass of the object. V is just the usual velocity vector, but omega is the angular velocity vector. So what does that mean? The angular velocity vector is a vector which points in the axis around which you are turning. And if the convention is that if this was my vector, right, I would be going clockwise around it. So how you can remember is you can get your right hand, you can find their axis. So if this is the axis that I'm rotating about, and you can curl your fingers around it. And if you look at your fingers, you can see that they would be going this way. So this would be the direction that you would be spinning around this vector if you had this angular velocity vector. So something you are totally unfamiliar from your A levels, but is this sort of vector which quantifies how you're spinning around it. So for the Earth, because the Earth is just rotating right through the middle, it's going to be turning around in this direction. So you can sort of imagine it as being 3D, because if you curl your hand, if you just point your hand in the direction which I've drawn, omega, and curl it around, you'll see that this will be direction in which the Earth will rotate. The last thing is the vector product, which I think, correct me if I'm wrong, is only covered in further maths, not maths. And like from checking the PAT syllabus, it's not on the PAT, but just for the point of explaining this question, because it could be something that could come up in interview, because at interviews sometimes you get asked questions which are kind of on unfamiliar topics, and you just kind of have to, explore your way through it. So a vector product, if you want to find the vector product of two vectors, it's sort of like multiplying two vectors together. But because vectors have lots of components, you can't just multiply like two numbers. So if everyone looks at my camera, in order to find the vector product of a vector A and vector B, I have my vector A, which is going to be, let me just write down, I'm going to show you how to find A times B. So in order to find A times B, its direction, because you can also find its magnitude, because you get a third vector and it has some sort of magnitude and it has some sort of direction, but we're just concerned about the direction here. So the direction is equal to, so you take your first vector A. This is going to be, I just had a bit of a moment to which I forgot how to do it. So this is going to be your vector A, your point finger on your right hand. It has to be your right hand. So your vector A is going to be your pointing finger, so this finger. Then your vector B is going to be the middle finger, and then vector C is going to be the product the vector product of A and B. So in order to find the direction, you have your vector A, you have your vector B, and you align your two fingers with A and B, and then you get vector C. So for example, if I just do a quick example here, if I have my vector A, this is a 3D drawing, I try. So I have a vector A here, and I have my vector B here. If I turn my hand, I will going to have, so this is my best drawing that I can do, even though I did GCSE art a couple of years back, that I'm going to have my middle finger point in this direction, and then my other fingers sort of kind of folded away. And my thumb is then going to point in the upwards direction like so, and that is equal to vector C. Again, it's just sort of a quick introduction to the vector product. The point is that I have this force, the Coriolis force, and it will have some specific direction, because it's going to be the force that makes these hurricanes turn. So if I consider some hurricanes in the top of the hemisphere, so in the northern part of the hemisphere, actually, I do need to draw the diagram. So if I consider a hurricane, I'll just, some air, right? And this air is going to travel, I just have a diagram that I have on my laptop. Okay, nice. So if I draw my core setup, and I'm going to have some velocity v, which is the direction with which the Earth travels. So if I just draw a bit of a side view here to make it obvious, this is the Earth, and this is my velocity v of the hurricane going upwards, because it's going along the Earth, because it can't, really leave the Earth, because it's like you can't go off to space. And then I have my angular velocity omega right here. So if I do the vector product by putting my nu right here and my velocity right here, if you point your hands in the way that I just showed you, you will find that the direction of the vector is going to be going in the direction pointing into the page. But because I have a minus in front, it's actually going to be pointing in the opposite direction, because the minus flips the direction of said vector. So what happens is if I draw, if I go back to my representation, just kind of twisting it around, the force is going to be acting in this direction. So this is going to be FC. Similarly, if I had some air just flowing down, by the same sort of calculation, the same sort of vector products, this one is going to, oh, sorry, no, I said this wrong. This actually will be going in this direction. Yeah, because this is going up. Let me just check it. Yes, sorry, I said the wrong direction. So yeah, this but before I put a minus in it, the vector is going in this direction, and then I put the minus on the vector product, which flips its direction. So here the the Coriolis force is acting in the right hand side, and here it is acting on the left hand side. So what happens in the northern hemisphere is essentially, let me just redraw the diagram. I'm going to have some sort of air traveling upwards, and as it travels upwards, it's going to slowly bend towards the right hand side, and the air traveling downwards is going to slowly bend towards the left hand side. Again, just to sort of review what I've said in the more kind of simplest terms I could put it, is I have this Coriolis force. You know, take it for granted that here it acts in this direction and here it acts in the left direction. But you can see that once I have the directions, I know that the air traveling from up is going to go left and the air traveling from down is going to go right. So you can sort of see that what's going to happen is air is going to go like this. Like, you know, because this air is going to go left. But if I start with some sort of kind of hurricane, you can see that it's going to twist in the direction that I have shown, which happens to be anti-clockwise. Which means that the answer to the question would be that the hurricane turns anti-clockwise. And if you want to make sure that you completely understand it, I'd recommend you do the same exercise, but do it for the southern hemisphere. So in this case, your velocity would be pointing actually down, right? Because first it was pointing towards the top of the earth, and now it's going to be pointing down. So all the directions are going to be flipped. So here instead, the one traveling from the bottom up is going to go like so. Sorry, from the middle down is going to bend like this, and the one traveling from the top is going to bend like this. So here you're going to have a slightly different circulation, which is going to be clockwise. So the point of this question, the point I'm trying to make, is you have this Coriolis force. It has this sort of vector product structure, and if you've done the vector product in further maths, this will make more sense to you. And because of this structure, because of the Coriolis force, it makes the hurricanes turn. And because it has this sort of vector product structure, it means that for the northern and the southern hemisphere, the hurricanes are going to spin in different directions. And as you can see at the top, it's anti-clockwise, and at the bottom is going to be clockwise, which is kind of cool if you think about it. Like, it's a myth that, like, if you kind of like, I don't know, flush a toilet or like just look at your sink, at the top is going to spin anti-clockwise and at the bottom is going to spin clockwise, because actually the force is just so negligible that it's not going to matter for you like flushing a toilet or something like that. But for hurricanes, because they're so incredibly huge, it does make them spin. So this is kind of this question. Again, don't worry, this is really hard. This would be more like an interview question where the tutor would guide you through it. Again, in my opinion, it wouldn't come up on the pad, but that's just my opinion. So kind of make sure that you roughly understand it. But there's lots of videos online about it. So yeah.
That's great. Thank you so much, Aggie. I completely agree with you. I think that strikes me very much as an interview question. We've also shared solutions with everyone, and they can watch the video back. So I think we can push on to our next question.
Yeah, so let me hide this. So the next question is about simple harmonic motion. And yeah, so they say it's possible to express the velocity as a function of time. And they want us to show that an object undergoing simple harmonic motion has the velocity as a function of displacement given by. So they start with saying that we can express the velocity as a function of time. And they want the velocity as a function of displacement. So in this case, it's mostly a math question, to be fair. So the one thing we know about simple harmonic motion is that the displacement as a function of time is a sinusoidal motion. So it is customary to express it as an amplitude times cosine, some angular frequency times the time. This could be a sine, it doesn't matter. Yeah. this is how, so this is the displacement. Oops. As a function of time. Okay, it's very laggy for some reason. Gonna give it a second, hoping that it's just because I'm streaming on Zoom. It's okay. Oh no, it's not happy. Okay, give me 1 second. If I don't fix it, I'm gonna switch to Aggie, and then I'm gonna figure it out.
It's not liking like you how you do it. It's not liking for me, but I'm okay to go through the next question if you want me to.
1 second. Just figure out what's happening, if something is happening. Hello.
I think with this one as well, Nina, simple harmonic motion is no longer explicitly on the PAT syllabus. So it would only be as a problem solving. This is from before the 2018
Yeah.
one. So it's not one I think is really interesting and great for us to discuss and very much essential knowledge, but I wouldn't worry too much if this is one that we skip over.
Okay,
That makes you feel better.
Yeah, Aggie go, and I can very quickly go through it right after. Sorry about that.
Yeah, I just need a minute because I'm just in the middle of answering the last pack question.
Not a problem at all. Actually, what I'll do while our two lovely undergraduates, or graduates actually, are discussing their problems is the fact that no, simple harmonic motion is not explicitly on the PAT syllabus. You can find the PAT syllabus online. You can have a look through it. We can't give you any more detail than is already there. It very much is the kind of thing that could come up as problem solving. And because we still use a lot of resources where this is a useful thing to learn, there is a problem on it here. But don't worry about it too much for the PAT itself. I hope that answers a few questions. And I think we're good to go back to Aggie.
So this is also a simple harmonic question, but like I think this would make quite a nice interview question. So I'll quickly go through it. Oh no, what did I just start sharing? That's that. Oh, I forgot to just plug in my iPad. There we go. There we go. So in my opinion, like it's still worth doing because it's quite nice. But on the other hand, I remember doing this question in my first year as I was preparing for my exam. So it's again quite difficult. So no worries if you don't understand it. But in my opinion, it would be quite a nice interview question. So, but I'm not a tutor, so I will not be interviewing you. So the question is actually, again, quite a cool one. And it says, imagine that a tunnel is constructed straight through the center of the earth. If a person were to fall into the tunnel, would they arrive at the other end? Describe the motion of the person and either explain why the person would not reach the other end or calculate the time it takes for the person to travel from one end of the earth to the other. So obviously, unless, like, in my opinion, because I've went through these courses and I've done this question before as my own preparation for my exams in first year, unless you've done electromagnetism and you know Gauss's law, or unless you know the answer to this question, it's going to be very, very difficult to do. But anyways, let's sort of, in an interview, for example, let's sort of go through what things you might want to mention. So this is the tunnel through the earth. Obviously, not physical, because how would you dig a tunnel through the earth? But, this is physics, so we are okay. We're sort of thinking of these things that will never happen. So we have this tunnel through the earth. And I guess the biggest thing is, what is the force going to be on the person going through the tunnel? Well, what actually the force is this: as a person goes into this sort of sphere of mass, the force acting on the person is only ever going to be the gravitational force equal to the mass contained at a radius smaller than the person. So what I'm saying is that the gravitational force between the person and the middle of the sphere is always going to be m is equal to MER times the mass of the person over the distance that the person is from the middle, which is just r, like so. And ME is the mass contained in the blue circle. So ME is going to equal to 4/3 pi r cubed times the density of the earth. Basically, what I'm saying is that when you are within a radius r inside. So if I just have a regular sphere like this, right? Obviously outside, you're used to the fact that your force is just equal to m of the Earth times the mass of the person over r squared. But as you're inside, for example, when you're at a radius r, so like here, you're not going to feel any of this mass. You're essentially just going to feel the mass below you, which in this case is just me r mp over r squared, which is exactly the formula, right? And because the tunnel is so thin, it's okay to not take into account that you have a tunnel and the mass is missing, because we're going to assume that's a really thin tunnel and the Earth is very, very big. So we have this equation for our force, which again, in my opinion, if you were doing for an interview, for example, they would just give it to you. So let's kind of substitute that in. So we get that F is equal to 4 over 3 pi r cubed over r squared mp, which is equal to 4 pi r over 3 mp, like so. So we have the force that a person is going to feel when it's at a distance r from the center of the sphere. And I forgot something. I forgot big G. Yeah, I forgot big G everywhere, actually. So we have a big G here, and we actually have a big G here. And I mean, if anyone, I don't know, has particularly too much time, oh, and I forgot rho here as well. So if anyone has too much time on their hands and wants to know exactly how this is derived, and I don't know, wants to learn some university physics, I don't know, I guess you just have to look up Gauss's law, and I guess then you could kind of like, that's just kind of the key word if you want to read more into it. But for the fact, you obviously don't need to know Gauss's law because that is like first year material at Oxford. So for now, just kind of take that this is the expression for the force, and then I just rearrange it for that to be the expression of the force. So you can see that my force is going to be proportional to the distance that I am from the center. So this is equal to r as I defined it. So as I get closer and closer and closer to the center of the sphere, my force is going to get stronger and stronger and stronger. Maybe you've heard of it. Because sometimes it's mentioned in some A-level textbooks that if I were to draw the gravitational force, it would be linear, and then it would fall down with the regular 1 over r squared that you are used to. It's measured in some A-level textbooks, not exactly how you get it, but just the fact that it's linear. But for now, this is just the expression. So we have a force which is proportional to the displacement. Well, if I have a force which is proportional to the displacement, surely I'm going to have some circular motion. Let's kind of check my logic. Well, if I'm here, I'm going to be getting pulled down because, you know, I'm going to be pulling down into the tunnel because the force always acts towards the middle. And when I'm here, I'm going to be getting pulled back, which is exactly the sort of thing that I have for circular motion. I have a force which is proportional to my distance from the midpoint, and the force is acting in a way to sort of push me through and then pull me back again, because as I get here, I'm going to have, again, the force pushing me, and assuming that I'm just dropped here because of the symmetry of the problem, what's going to happen is I'm going to go all the way here, and at this point, my velocity is going to be equal to 0 because I start with some 0 velocity here. I speed up here, have a maximum speed here, just as regular simple harmonic motion. Then I slow down here because I'm being pulled back, and here I end up with velocity 0. And then once again, the process repeats. I get pulled in, I slow down, I get velocity 0, and, you know, also so on, so on. So you can see that I'm going to have simple harmonic motion. And yes, the person's going to reach the other side, and then I can now find the time. But with simple harmonic motion, you know that the time is going to be equal to the period for the person to go there and back. But we just want the time for the person to go one way, so we are looking for half the period, because the period would correspond to going down and going back up. So let's kind of make this look simple harmonic motion. We know that the force is equal to m person times the acceleration. So if I just equate these two equations, I get that mpa is equal to 4 pi gr over 3 mp rho. So my mps cancel, and I get a is equal to 4 pi g over 3 rho r, like so. And I'm sure that you have heard of the, actually, sorry, I should probably have a minus here because of what I've just explained. The force that you get using Newton's law at A-level doesn't have a minus sign because you always know the direction is towards. But for the purpose of, you know, keeping it looking simple harmonic motion, I'm going to say that it's a minus just because simple harmonic motion always has a minus, and I know this is simple harmonic motion. So I get that, yeah, this is what my acceleration is equal to. Yes, so obviously I have the density of the Earth, which is something that I will need. So let's quickly write what the density of the Earth is. So it's going to be the volume of the Earth, which is 4, which is going to be the mass of the Earth, me, over 4 over 3 pi re cubed. Just put that into my expression, so I get A is equal to minus 4 pi g over 3 times me over 4 over 3 pi re cubed r. And finally, this is just minus gme over re cubed r. So we have an expression for the acceleration, which we got by kind of knowing how the gravity varies inside the Earth. Nice. But we know from simple harmonic motion that the definition of acceleration in simple harmonic motion is that A is equal to omega squared r. So from here, we can see that omega squared is equal to gme over re cubed, like so. And then we get that omega is equal to the square root of gme over re cubed, like so. So that is going to be the frequency of our motion. And we know that the time period is equal to 2 pi over omega. So we got that the time period is equal to 2 pi, the square root of re cubed over gme, like so. And because we want the time, I forgot if the question asks how long it would take to go back. Let me just quickly check. So the question asks, so the question asks for the time for the person to go just from one end. So from the top to the bottom, which would just be half a period. So the time taken would equal to the period over 2, which is just pi, the square root of re cubed over gme. So kind of just sum up the question because it was quite difficult. If we knew what the force looked like inside a sphere, then we could just, using the regular force equations, we could just kind of come up with this and see that it is indeed simple harmonic motion. But the hard part of this whole question, obviously, once we've done that, it's just kind of doing things that are in A level. But the hard part of this question is obviously knowing this, which again, if it was an interview question, I assume the tutor would really help you get, would really take you on the right lines to kind of get there. But yeah, so this is kind of that question. I'll hand over to Nina for the last one.
Thank you so much. This is perfect time. We've got about 5 minutes for this final question. And
Nice.
then I will take over and talk a bit more about next steps and the path in general. So over to you, Nina.
Yeah, very quick remark for the simple harmonic motion, just because it's good practice. As I said, we do have an expression for the displacement. As they say, so this is as a function of time. As they say, we can get the velocity as a function of time by differentiating, which would be sine omega t. What they want us to find is v of x. So this means an expression for the velocity as a function of x. And if you look at this, what bothers you is the time. So what you have to do is substitute the time as an expression of x into here, right? And this is what you would usually do. You would express t as a function of x to substitute here. But right now you have cosine and a sine. So whenever you see something like that, sine square plus cosine square equals 1. So use that. Read through the solution. It's a nice, neat problem. But yeah, if it's not on the syllabus, yeah, maybe not for the path necessarily. I just want to see. Yeah, so the last problem, it's not necessarily a short one, but let's try to go through it relatively quickly. So we have a tank. Actually, this will be inconvenient in a bit. So we have a tank which is falling down. It's going to fall onto the ground, but some distance away from it, there is a convenient landing spot. So what the people on the tank decide to do is to fire shells horizontally away from the tank so that by Newton 3, they can push the tank towards the landing spot. We are given, and yeah, the question is how high in the air, let's call this H, must the tank be so that it can actually reach the spot. So we are given some numbers in the question. We have the projectiles which are being thrown from the tank. Their mass is 10 kilograms. The velocity with which they leave the tank is 1750 meter per second. Usually when you have the problem like that, I do write them down so that you can show the examiner what your how you will denote those parameters. Then you have the time between shots. So they fire one projectile and they fire the other, and the time between the two. I'll call delta T is 3.5 seconds. Then we have the mass of the tank, which is the big mass here, which is 22 times 10 to the third kilograms. And finally, we have the terminal velocity of the tank. So we assume that as the tank is falling, because it's falling through a fluid, air, at some point it reaches terminal velocity. So it's falling down with a constant velocity. Definitely look up terminal velocity if you haven't heard of it. And this is 33 miles per hour. And this is a good opportunity to convert to SI units as always. So this is, oh, no. So this is roughly 14.75 meters per second. So to move horizontally, there needs to be a horizontal force exerted on the tank. This horizontal force comes from the projectiles being fired every 3.5 seconds. So we see that we will need some sort of an expression for force, and something suspicious we saw, which we don't usually see in problems, is delta T. This should be your clues to use that a force applied to a body. In this case, the force coming from the projectiles is the change of momentum over the change of time. So this is the first important thing you are expected to think of when you read that problem. And again, I think the clue is that you have an interval of time. So the average force which the projectile masses will be exerting would be their mass times their velocity, because this is their change in momentum over this delta T we're given. So yeah, you can plug in numbers, and this is 5 times 10 to the third Newton. So this is the averaged continuous force. So it happens every few seconds, but if you average over a longer period of time, it would be the equivalent of a continuous force of 5,000 newtons being exerted on the mass. So this is the other concept, that discrete chunks of forces could be viewed as a continuous force. And you do this because then you can apply Newton's second on your tank. So you have a continuous force applied on the tank in the opposite direction, right? So in this direction, you have an F, you have its mass, so you can find its acceleration. And this puts you in a very good position to use your Suvat equations, because now you have some acceleration horizontally, you have a constant force, constant velocity going downwards. You want some height. In the problem, you're also given in the main text this distance, which I'll call L, and it's given as 0.5 miles. So yeah, again, be careful where you're given what information. And this is about 800 meters. So yeah, at this point, it's just a Suvat problem. These were the important concepts. Yeah, so you have your acceleration of 0.25 meters second squared. And looking horizontally, you can say that this L, which the tank has to travel, will be its initial velocity times the time plus a half AT squared. This is 0 because we assume that horizontally it is initially only falling downwards, so horizontally it doesn't have any velocity. We have the acceleration, we have this L, therefore we can find the time. It turns out that the expression is 2L over A. square root. And this is 80 seconds. So horizontally, we know that it has to travel those 0.5 miles. And if it is successful, it would need 80 seconds to do so, right? The question is how high the tank must be initially so that it actually reaches this landing spot. And so we look vertically, and we know that this height, it has to go through, it goes at a constant velocity, so this height would be just equal to v times t. T is those 80 seconds. V is the terminal velocity we're given in the problem. So finally, if you just plug that in, it turns out that the height at which it has to be is at least 1,200 meters. Yes. They, at the end of the problem, they did they ask about assumptions? No, they don't really ask about assumptions, right? I heard this question. Yeah, they just ask about height. Yeah, I guess it's worth noting as you're writing the problem, what do you assume? During interviews, they absolutely love asking about what assumptions you've made and comparing to an actual situation. So in order to be able to assume, like in our formulas, when we use the F equals ma, we assume that the mass of the tank is constant. It doesn't change, whereas you're firing projectiles, which were on the tank before that, but the mass of the projectiles is significantly smaller than the mass of the tank. So this is one assumption we're making. We made the assumption that the initial horizontal velocity is 0, but if the tank is falling from a plane, the plane was moving horizontally, so the initial horizontal velocity might not be 0. So this is just another assumption we made in order to find the time of flight. And something else you might mention is air resistance sideways. So vertically, we do take account of the fact that the tank is falling through air because it reaches the terminal velocity. However, horizontally, we don't account for a friction force going the opposite direction. So yeah, this is the question pretty quickly. I will answer in a bit more detailed questions in the Q&A. So even if you have a silly question, do put it down because this was very quick.
Thank you so much, Nina. As you can see, Aggie has already left as well. She's gone to another event. And that is because we are very much reaching the end of our preparing for the PAT course. That was our final problem solving session. What I'm going to do now until 8:30 is three things. I'm going to address the questions we have had about the PAT in the Q&A so far. And I can see that they come into a couple of quite general categories. So I'm going to be able to do that in quite a systematic way. Just listen out and your question will probably be answered. That should take me 5 minutes or so. I'm then going to show you a couple of slides that are going to take you through our admissions timeline, where we are at the moment and what you could expect next. Our admissions criteria, which will really help you drill into your UCAS statement. And in fact, I'll look at that in a bit more detail, and also a little bit about our interviews. That should take me another 5 or 10 minutes, leaving us time for any additional questions at the end. I hope that makes sense. So, looking at the questions that we have had so far, we have had a lot of questions about marking. People always really like to ask us specifics, like, if I write this, will I get the marks? If I do this, will I get the marks? I can tell you now, we cannot give specific answers for this, but for a really good reason, and a reason which is beneficial to you as candidates. Our solutions, or the solutions that you provide to our academics, are all marked based upon their individual merit. They are based on the understanding that you show of the question and how many marks your solution deserves. Our academics will mark in groups to make sure that their marking is consistent across the entire year group, and your paper will be marked by an academic in the subject that you are applying for. So for example, if you're applying for physics, your PAT course will be marked by physicists who are looking for your understanding of physics in these questions and marking accordingly. If you are applying for materials science, your PAT test will be marked by a materials scientist, and they will be marking based upon the materials science capabilities that you show. Therefore, we cannot answer specifically, will this get me a mark? Because it's a much broader question, but this is positive because it means the examiners are looking for your understanding and looking to give you marks. As a general rule, you must show working if working was required to get to your answer. If you wouldn't be able to just get to the answer, you're not going to get full marks for just giving the answer. And that's our kind of general rule. But like I say, I think that addresses this questions we've had about specific marking schemes. The next general topic that we've had is the online calculator. It's upsetting people. We know it's a big change. All test centres will be using the online calculator, and that means that all of you are dealing with the same slightly strange calculator, and that in itself is great. You're all in the same situation. All of you will be providing answers from this same calculator, and our markers are really aware of the fact that this is new. I would recommend you practice with this calculator by having it on screen at all times when you're solving problems and having yours as a comparison. I'd also suggest don't need the calculator that much throughout our test. Obviously, there are times when you do. I'm not for a second suggesting this is a non-calculator paper, but it's not as calculator heavy as you might be panicking and thinking it is, and you should be absolutely fine. The general rule for the calculator is that it's a reversed operations calculator. It's quite an old-fashioned format. So for example, if you wanted to find the sine of 30 degrees, you'd put in 30 and then press sine. That's kind of your general rule. Like I say, practice, get used to it. It is weird. You're not the only ones finding it weird, but you're all addressing the same issues. So again, don't stress about it too much. The third sort of common theme that I'm seeing through this are, how do I prepare? Where are the resources? What can I do? Here, for a really good start, have a look on our course materials page where you've got all of the problems that we've used, all of the solutions, all of the videos. Those are all great places to start. The PAT syllabus, the PAT past papers. And then I always quite like, as an exercise, try somebody else's exam. If you're an A-level candidate, have a go to Scottish Advanced Higher paper, have a go to US SAT 2 test. Okay? But all of the resources, we email you every time we do a PAT with a list of suggested resources. I've not got anything extra to give you beyond what we suggest in that email that comes round. And then the fourth sort of general category I find is about the spec or things that can specifically be asked. We've had a few of those, some have motion radiation. Our syllabus, as given on the website, is what we expect you to know and to know well, that we can ask you a lot about. That doesn't mean that's all we can ask you about, because a lot of other questions can be coached in terms of problem solving. It gives you a good idea and it's accurate from 2018. I cannot give you more detail than is on that syllabus. That is what we tell you you need to know. That is what your PAT test will be based on. So I hope that addresses those sort of PAT spec questions as well. Those are the 4 general themes I can see so far. I think that addresses those. I'm now going to share my screen, move on to our second part, and give you some more details. So hopefully I can find my screen. I currently have a lot of different screens. Okay, you should be able to see the application timeline. And what you should also be able to see is that we are rattling through this application timeline. So we have worked our way through the summer. You may well have started working on your UCAS form. You may well have started to get to grips on the PAT. Don't worry if you didn't. Not everybody makes their decision really early. Some of you are working on this now. you've still got a month until the PAT. You've still got plenty of time. But it is worth noting some deadlines. Your UCAS form is due in on the 16th of October. So you will have to have applied to Oxford before you actually sit the PAT, which is on the 20th of October. I'm afraid I do not know what time the PAT is at. That information has not yet been passed to me. After that, you have a little bit of a lull, because after that, you wait to find out if you've been shortlisted and if you've been invited to interview. Our interviews are being held in the first couple of weeks of December, and there is an online draft timetable of interviews if you're looking to find out exact dates. All you need to do is Google Oxford draft timetable interviews, and you will find that out. And then decisions will be made in January. Good to see that we're getting a few more questions coming through. I'll address those after this slideshow, so keep them coming if you're still looking for things. But what I'd like to draw your attention to is something you might not have seen before. These are our physics admissions criteria. These are the 5 things that we're looking for in a successful candidate. And these are things that we look for in your PAT test, in your teacher reference, in your UCAS personal statement, and in your interview. So our questions in the PAT are designed to give us insight into these 5 criteria. The questions that you're asked at interview are designed to test these 5 criteria. And when we're looking through references and personal statements, these are what we're looking for. So first and foremost, we are looking for motivation. The fact that you are all here shows us that you are motivated to study your subject. I should point out this is physics specific, but it applies quite generally to the other courses as well. So you have to want to study a subject if you're going to be studying it at university. Okay? We're then looking for your mathematical ability. We're looking for your ability to express physical ideas using mathematics. And if you now think back to some of the PAT questions we've been taking you through, you should see that that's something we're looking for. Okay? The third thing we're looking for is your reasoning ability, and this is obviously really closely related to your mathematical ability. We're looking for you to be able to analyze and solve problems using logic and critical approaches. So these slightly strange problems like the tunnel that's through the earth, we're looking for you to actually think about it and go, okay, well, what do I know? Where do I want to get to? How can I apply this? Okay, so this is what we're looking for in terms of your reasoning, how that relates to your mathematical ability. And then a huge part of what we're interested in as well is your physical intuition, your ability to actually think about how things affect other things and their physical relationship between each other. And that might explain to you why we have some of these slightly strange questions that aren't just straight, solve this equation for me, because we're interested in how you relate physical systems to each other. Okay? And then the 5th and the final thing we're looking for is your ability to communicate. And that actually means how you communicate mathematically as well as how you communicate orally. Okay? Mathematically, and might I add, not just writing maths, writing explanations that go alongside your maths. So jumping back a bit to when I was talking about our marking, the way that you communicate in the PAT is an important part of how successful you are going to be in gaining those full marks. So those are our admissions criteria. I will share this set of slides with you tomorrow as well, so that you can think about this in your own time, because obviously today is quite a whistle-stop tour. Now, we look for the admissions criteria in your PAT test, but you all also have to write a personal statement. At Oxford, when we're looking for a personal statement, we're looking for it to be roughly 80% academic and 20% extracurricular. We completely understand that personal statements are written for all of the universities that you are applying for. And so, although this is our preference, we understand if you don't meet it exactly, please don't start counting sentences and making sure that 8 out of every 10 of your sentences are academic. That's fine. We're just sharing this for you as this is what we consider to be a really successful personal statement. Our academics here also include super curricular activities, which we would consider to be very different to extracurricular activities. So supracurricular activities are activities like coming along to the Preparing for the PAT course. They're activities you do about your subject, which are not provided for you by your school. So they might be reading journal clubs, going to lectures, things that, again, demonstrate your passion for physics, going back to those physics admissions criteria. Some general tips: make sure you plan it. Do not undersell yourself, okay? If you're really good at physics, tell us about your prizes. Be honest. You will be caught out if you say that you absolutely adore something. Like, it's always the classic example. If you say you're really keen on sailing and you're applying for engineering, they'll probably expect you to have some idea of how a boat can sail into the wind, for example. It's important to be honest. And then some more tips on how you write them. Be reflective and show, don't tell. So you can be really clever with your personal statement in what you demonstrate in what is a really short thing. Yeah, it's a really short piece of writing. You don't get much space to sell yourself. But if you think about the way that you talk about activities, you can squeeze in a load of information that really shows us things rather than just tells us. So say, for example, you have attended a lecture at a local university. I'm not saying you have to have, but as an example, let's say you did that. What you could tell us is that you found out about this university lecture through signing up to a mailing list. You organized the trip to it yourself. And then you're showing us, not only did you do a supracurricular activity, but you arranged it yourself because you were dead interested in physics. If you do other activities as well, please don't worry if your personal circumstances mean that actually you spend a lot of time, for example, caring for others, or if you have a part-time job. Use these to demonstrate some of those other criteria for us. If we're interested in your passion, you can tell us about how you work your studies around your other commitments. You can tell us about how you have to choose your activities really carefully so that you can meet your caring commitments, but still demonstrate an interest in physics and still learn. So please don't feel that we're expecting you to have done lots of activities. A bit like your PAT is marked as an individual piece of work, your personal statement and what we're looking for are based on you as an individual, the opportunities that you have had and how you have made the most of them. For some people, there will have been more opportunities. They will have made more of them. For some people, there have been fewer opportunities. And as long as they've made the most of those, that's great. Okay? Ask for feedback, check your spelling and grammar, good general tips. Now, assuming that you sit the PAT, you do well, you write a great UCAS statement, and we shortlist you, you may well be invited to interview. Interviews are held online, and you will often have 3 interviews at 2 colleges. They're similar sort of content and level to the PAT, but they're really designed to think about those criteria, how you think about physics, how you communicate it, what your physical intuition is, and those kind of things. Okay? Do some preparation. Just talk to people. So we're not looking for you to have done huge amounts of interview practice. Not everyone has that opportunity. But what you can practice is talking to yourself as you solve physics. So you've seen loads of people over the last 8 weeks explain their solutions to you as they do them. That's all you need to be doing. You need to be saying, okay, I know that this equals this, so I can do this. So speaking aloud. That is my whistle stop, what I wanted to tell you. I'm going to stop screen sharing, have a look back at some of the questions I've been asked, and I've got 10 minutes to cover those. I really hope this has been useful for you. So let's have a look back to, okay, first one I can see is from the online PAT. I see that there are questions on the screen. What's going to be on the actual paper? There is also an example answer paper. So if you are on the Preparing for the PAT admissions page, let me share this in the chat for everyone. If you are on this general page, there is a test preparation and materials tab. You will be able to scroll down that, and there is there's a video, of about the online PAT. There is a link to the online PAT through which you can access the online calculator, and you can access it as many times as you like. And there is also below that link an example answer booklet. Okay, let's see if there's anything else that I haven't got. Alternate calculator being approved. I'm not sure of exact dates for that. If you haven't heard anything back, you can email the test centre. How much weight do you give to each? The PAT, the interview, the personal statement, and the reference. So for those individual weights, you can have a look at our admissions reports. I will find you a link to those. And again, a lot of these things that I'm sharing with you at the moment are links that I share in the PAT emails that come around every single week. So there are loads of them in here. So actually, I'm going to need to show you that because our website is not currently open. So I will share the admissions reports that you can go through and have a look at, like what the standard scores were, how things were weighted, and you can have a look at that tomorrow. To get a copy of the calculator without doing the practice test, just open the practice test and don't do anything. Just open it on the webpage and then you'll have the calculator open. Dead easy. How important is our choice of college on the UCAS form? Honestly, not important at all. Feel free to select a college if you strongly have a preference, but there's absolutely no obligation. If you select a college and it turns out to be really oversubscribed for physics candidates, you'll be allocated a different one anyway. And if you interview and are amazing, but so was everybody else who interviewed at your college, you'll be spread around anyway. So put a choice of college if you feel really strongly about it. If you don't worry about it. I'm afraid I do not know exactly where the option is on the UCAS form, but I do know you can submit an open application. But because I'm not an applicant, I can't get into that part of the UCAS website to see what buttons you would press. There is not an engineering specific Oxford PAT or UCAS session. So the PAT test is exactly the same, regardless of which set you are doing it on, and hopefully that information you've had about the UCAS form, what we're looking for, should translate pretty well over. Again, for looking at things like how your GCSE scores are affected, those admissions reports that I share links to every week have got all of those details. They are quite dry reading though. I would say don't worry about it too much. Again, for what you write down, have a look at the sample answer paper, and that will give you a really clear idea of exactly what you'll be doing. They've got things that you circle for the multiple choice. So just have a really good look at the resources so that you know what you've got there. I don't have specific links for engineering. It will probably take you as long to find them as me. So if I was you, I'd have a very quick look for Oxford Engineering Admissions Report, and you should get it through there. And then we've got find info on the general structure of the upcoming PAT. I don't think I can give you any more information than I've already given you. So you can look at last year's, you can look at the sample PAT. There's not too much more there. It shows you which ones are multiple choice and all those things. So don't worry too much about that. The person who said, if I find it difficult to see questions on a screen, can I ask my school to accommodate me? So we do take access requirements, but that should all have been done already. So if you have access requirements, you need to talk to your school really quickly because that should have been done at the same time as processing your test application. Okay. And then in terms of reduced offers, do you mean contextual offers where your grades would be lower than specified? Not so much, to be honest. The grades tend to be pretty high, but what you might find is a little bit of flexibility within that once you get there, but you are still really looking at those A's and A stars in maths and physics. Sorry guys, I know it sounds a bit weird just because I'm scrolling to make sure I don't miss anything. I've got a question that just says maths and graphs. Might need a little bit more information to be able to help you with that one, but I'll give you a shot if you type a bit more information. Got a few questions about time management. I would say as far as this goes, it's not really that different to any other question. Have a look at some past papers so you know roughly how many questions you have to answer in how much time. And then you can start thinking about pacing yourself, like, well, I'll get through the multiple choice questions more quickly, leave myself longer for those written answers. So it is a case of looking at a couple of past papers, so the syllabus has been the same since 2018, and using those to work out how you think you could best allocate your time. You might even want to have a look at, for example, how many marks there are, divide the number of minutes you get by the number of marks, and then you'll have an idea of that. The PAT does not get harder every year. It is fairly similar throughout. So again, the admissions report tell you how we use them every year. In terms of what the actual offers are, it's not usually 3A stars. You can have a look on our website at the admissions requirements and you can see what they've offered. You can also usually click through to uni stats, which is quite interesting because that will show you what the actual grades that people had were, which is quite a useful thing to be able to do. To do the question about spare sheets of paper, given an answer booklet, honestly, I'm not totally sure, but I would imagine if it's scanned, you'll be fine. There's significant amount of space on it. I can't see anyone discriminating against you. Can't say 100% sure, but I guess it would be like any other exam. I am seeing somebody asking about the button on the calculator. Can you convert from fractions to decimals? No, we're mean. It's a really old-fashioned calculator with really limited use. But as I've said, nobody has that function available to them. So you don't need to worry too much. It's not just you who's had that function removed from you. Okay. Offers being higher than that stated on the website? No, offers will not be higher than they are on the website. In terms of, I think I've had a couple of questions where people have asked, what do you do if you don't remember the equations? What if you don't understand what the question was? A great deal of that is working through it for yourself. So if you don't understand the question, give it a shot. Okay. But also don't waste too much time. So this is where the knowing roughly how long you've got for a certain number of marks comes in. Don't spend too long doing something you don't understand. If you don't remember an equation, if it's something you can make a smart guess at, for example, if you know that it's an inverse square law, you could use that relationship and miss out the constants. If you just don't remember it completely, you might need to get creative in what you can do using other equations. Okay. And then I've got a couple of quite specific questions. So I'm going to rattle through those and take about another 5 minutes. If you're asking me specific questions about what's on the syllabus, please check the syllabus. I'm not going to be answering those now that we've had this discussion. In terms of if your PAT score is lower than the mean, again, these are questions. Have a look in our admissions report if you really want to dig into those specifics of what score do you need. And they'll tell you about the fact that your PAT score forms part of it. They'll also just give you an idea of the sort of general question. I see the person who asked me about maths and graphs has expanded on that. Great, thank you very much. Regarding maths, does the PAT really like graph work? There is a significant amount of graph work, and if you think back to our admissions criteria, that is very much because it demonstrates how you think about systems. It shows your mathematical ability, your physical intuition, and your ability to communicate those mathematically. So there will be quite a few graph questions in there. And then I think I've got one more. If given an offer and I do 4 A levels, including further maths, what's the typical offer and typically what 3 will it be? Okay, honestly, this depends what A levels you're taking. So your offer will only ever be on 3 A levels. I can tell you that now. You're not going to get an offer which has 4 letters in it. You will be given an offer based on 3 A levels. If you are taking maths, further maths, physics, and something else, regardless of what the something else is, your offer will be on maths, further maths, and physics. If you are taking maths, physics, and 2 others, then it's up to the individual tutor what your third one might be. So say, for example, you were taking maths, physics, chemistry, and biology. Maybe at one point you wanted to do medicine, but now you've decided that actually physics is the best. Your tutor could offer you on maths, physics, and chemistry, or maths, physics, and biology, depending on what they think is best. So your offer will always be on maths and physics. If you offer further maths, it will be on maths, physics, and further maths. In terms of your final preparation, keep up the hard work. I'm going to send you all out an email tomorrow morning, which gives you a list of all of the information that you might need over the next couple of weeks. Keep practicing. Make sure you have had a really good look at all of the past papers. Make sure you have a rough idea of how many marks you are going to answer in each question. Okay, anything about requirements, equipment, technical things, those will all be on the test. You don't need me to answer those for you. If there are any questions that I have not answered, you can contact me on my email address that comes round, you guessed it, in the Pat email that comes round every week. I'm going to keep sending you those, if nothing else, just to wish you good luck. I have shared one more thing in the chat for you today, which is our course feedback form. Please do feel free to click through this if you've got a second now. Your feedback on this course is incredibly helpful because it tells us what you find useful, which means that next year we can do more of that and make the course more beneficial for you. If you don't have time to do it now, you guessed it, I'm going to be badgering you by sending you this link every week until you sit the PAT. So please do send them through. In terms of physics questions via email, a little bit more hit and miss whether I'm going to answer them. It simply depends how much time I have. I may well direct you towards solutions or back to your teacher. I hope that has answered all of your questions. It has been such a pleasure being part of the PAT course with you this couple of months. I hope it's been useful and I wish you all the very best. Thank you so much, everyone, and goodbye for now.